In 1977, two spacecraft left Earth on what was supposed to be a short tour of the outer planets. They weren't built to explore the edge of the solar system. They weren't designed to survive for decades. And yet, nearly 50 years later, Voyager 1 and Voyager 2 are still sending data back from a place no spacecraft had ever reached before. They're now so far away that their signals take more than 20 hours just to reach Earth. Every command sent to them is a slow, careful exchange across billions of kilometers. And what they've found out there has changed how we understand the boundary of our own solar system. For a long time, scientists thought they had a decent idea of what that boundary looked like, a smooth transition where the sun's influence simply faded away. But the Voyagers didn't find anything that clean. Instead, they detected turbulence, strange magnetic behavior, unexpected radiation levels, and something that sounds almost impossible, a kind of faint, persistent hum coming from interstellar space itself. These spacecraft weren't supposed to see any of this, but because they kept going, they ended up becoming the first probes to actually touch the space between stars. And what they sent back isn't just data, it's our first direct look at what lies beyond the sun's reach. Back in the early 1970s, NASA wasn't planning to send anything to the edge of the solar system. The goal was much more specific and much more limited. Scientists had noticed a rare alignment of the outer planets that only happens about once every 176 years. Jupiter, Saturn, Uranus, and Neptune would line up in a way that a single spacecraft could visit all of them using gravity assists. That opportunity set everything in motion. Instead of launching separate missions to each planet, engineers realized they could take advantage of this alignment to build a kind of cosmic shortcut. A spacecraft could fly past Jupiter, steal a bit of its orbital energy, and get flung towards Saturn. Then repeat the process again and again. It would save years of travel time and massive amounts of fuel. That idea became the foundation of the Voyager program. Two spacecraft were built, Voyager 1 and Voyager 2. Despite the numbering, Voyager 2 actually launched first, on August 20th, 1977. Voyager 1 followed a couple of weeks later, on September the 5th. The naming came from their flight paths, not their launch order. Voyager 1 was put on a faster trajectory so it could reach Jupiter and Saturn sooner. At the time, no one expected these spacecraft to last more than a few years. The mission plan was simple: get detailed data from Jupiter and Saturn, maybe extend Voyager 2 to Uranus and Neptune if things went well, and then accept that the spacecraft would eventually go silent as their power ran out. The design reflected that expectation. The onboard computers were extremely limited by today's standards. Each Voyager has less memory than a basic calculator. Data rates were slow. Every command had to be carefully planned and uploaded in advance because real-time control wasn't possible even back then. But the parts that mattered most, the ones that determined survival, were built to be incredibly robust. Instead of relying on solar panels, which would become useless so far from the sun, both spacecraft were equipped with radioisotope thermoelectric generators, or RTGs. These devices convert heat from the natural decay of plutonium-238 into electricity. No moving parts, no reliance on sunlight, and a steady, predictable power output that slowly declines over decades. That single design choice is one of the main reasons the Voyagers are still alive today. The spacecraft were also built with redundancy in mind. Critical systems had backups. Instruments could be turned off if needed. Engineers even included ways to reprogram parts of the system remotely, something that turned out to be essential decades later when unexpected problems started showing up. Still, none of this was meant to support a 50-year mission. What really made the difference was how carefully the mission was managed over time. As the spacecraft traveled farther from the sun, engineers began shutting down non-essential systems to conserve power. Heaters were turned off, even when it meant instruments were operating in temperatures far colder than they were designed for. Some components kept working anyway. It's not that the spacecraft were indestructible, it's that they were adaptable. And that adaptability turned what should have been a short planetary mission into something much bigger. After completing their flybys of the outer planets, both Voyagers were still moving fast, tens of thousands of kilometers per hour, and heading outward. There was no reason to stop listening, so NASA kept the communication lines open. At first, it was just about seeing how long they could last. Then something interesting happened. As the spacecraft moved farther away, they started entering regions of space that had never been directly measured before. The solar wind began to behave differently. Particle densities changed. Magnetic fields shifted in ways that didn't quite match predictions. Suddenly, the Voyagers weren't just leftovers from a finished mission. They were the only instruments humanity had in a completely unexplored region. And that changed how people started thinking about them. Instead of shutting them down once their primary objectives were complete, NASA extended the mission. Then extended it again. New teams of scientists got involved, focusing on heliophysics, the study of how the sun interacts with space beyond the planets. The spacecraft kept going. By the early 2000s, both Voyagers were approaching a region called the termination shock, where the solar wind begins to slow down dramatically as it pushes against the interstellar medium. This wasn't part of the original mission plan. No one in the 1970s expected these spacecraft to still be working at that distance. But they were, and they were about to become the first probes in history to directly explore the boundary of our solar system. That's the part no one planned for. Even today, engineers are still finding ways to keep them alive just a little longer. Power levels continue to drop, so more instruments get turned off every few years. In some cases, backup thrusters that hadn't been used in decades were brought online again to maintain communication with Earth. Each adjustment buys a bit more time because every extra day means more data from a place we can't reach any other way. And the farther they go, the more unexpected things they keep finding. To understand how the Voyagers got so far, you have to look at the one trick that made the entire mission possible: gravity assist. At a basic level, it sounds simple. A spacecraft flies close to a planet and uses its gravity to change direction and speed. But what's really happening is more subtle. The spacecraft isn't just falling toward the planet and then escaping. It's borrowing a tiny bit of the planet's orbital energy around the Sun. Think of Jupiter moving around the Sun at about 13 kilometers per second. When Voyager 1 approached Jupiter in 1979, it didn't just get pulled in and slung outward randomly. It was carefully aimed so that relative to the Sun, it would leave the encounter moving faster than it arrived. The energy came from Jupiter's motion, not from the spacecraft's engines. Jupiter slowed down by an amount so small it's basically impossible to measure. Voyager sped up by a huge amount relative to its size. That's the trade. And once you understand that, the rest of the mission starts to make sense. Both Voyagers used this technique, but in slightly different ways. Voyager 2 was put on a path that allowed it to continue beyond Saturn, heading toward Uranus and then Neptune. That required a very precise trajectory. Miss the angle even slightly, and the chain would break. Voyager 1, on the other hand, was given a different priority. Scientists wanted a close look at Saturn's moon Titan, which meant adjusting its path during the Saturn flyby. That decision gave up the chance to continue on to Uranus and Neptune, but it provided detailed data about one of the most interesting moons in the solar system. So from that point on, the two spacecraft split into completely different missions. The Jupiter flybys were the first major test. Before Voyager, images of Jupiter were relatively low resolution. Scientists knew about the Great Red Spot, some cloud bands, and a few moons. But when the Voyagers arrived, the level of detail changed everything. They saw storms within storms, complex turbulence patterns in the atmosphere that hadn't been visible before, lightning flashes on the night side of the planet, thin, faint rings that no one had confirmed existed, and around the moons, things got even stranger. Io, one of Jupiter's moons, turned out to be covered in active volcanoes, not ancient ones, ongoing eruptions, plumes rising hundreds of kilometers above the surface. It was the first time active volcanism had been observed anywhere beyond Earth. That discovery alone reshaped how scientists thought about small planetary bodies. Heat wasn't just something left over from formation. It could be generated through gravitational interactions, in this case, from Jupiter constantly stretching and squeezing the moon. Europa showed something different, a smooth, cracked surface that hinted at a subsurface ocean. Ganymede revealed a magnetic field of its own. Callisto looked ancient and heavily cratered, preserving a record of early impacts. All of that came from one planetary flyby. But the mission didn't stop there. After Jupiter, both spacecraft headed towards Saturn. Voyager 1 arrived in 1980, followed by Voyager 2 in 1981. Saturn's ring system turned out to be far more complex than expected. Thousands of thin ringlets, braided structures, and gaps shaped by small moons, acting as gravitational shepherds. Titan, the moon that Voyager 1 prioritized, was completely covered in a thick orange haze. Visible light couldn't penetrate it, so the surface remained hidden. That might sound like a limitation, but it revealed something important. Titan had a dense atmosphere, rich in organic molecules. Later missions would confirm lakes of liquid methane on its surface, but Voyager was the first to show that this moon was something special. After Saturn, the paths diverged completely. Voyager 1 used Saturn's gravity to tilt its trajectory upward, out of the plane of the solar system. That move effectively set it on a direct path toward interstellar space. It wouldn't visit any more planets, but it would get there faster. Voyager 2 continued outward. In 1986, it reached Uranus. No spacecraft had ever visited it before, and none have since. The planet looked almost featureless at first glance, a pale blue sphere with very little visible activity. But the data told a different story. Uranus has an extreme axial tilt, essentially rolling around the Sun on its side. Its magnetic field is offset and tilted in a way that doesn't align with the planet's rotation. Its moons showed signs of past geological activity, and its ring system, again, was more complex than expected. Then came Neptune in 1989, the final planetary encounter. Neptune turned out to be surprisingly active. Despite receiving very little sunlight compared to Jupiter or Saturn, it had strong winds, the fastest in the solar system, reaching over 2,000 kilometers per hour. A massive storm system called the Great Dark Spot was observed, along with high-altitude clouds casting shadows below. Its moon Triton was even more unusual. It orbits Neptune in the opposite direction of the planet's rotation, suggesting it was captured rather than formed there. Voyager 2 detected geyser-like eruptions on its surface, likely driven by nitrogen ice. After Neptune, there were no more planets to visit. Voyager 2, like Voyager 1, was now on a one-way path out of the solar system. And here's the key point. By the time both spacecraft finished their planetary tours, they were already moving fast enough to escape the Sun's gravity entirely. The gravity assists hadn't just sped them up, they had set them on escape trajectories. That means everything that came after, the crossing of the heliosphere, the entry into interstellar space, was only possible because of those earlier encounters. Without Jupiter's initial boost, neither spacecraft would have made it very far. Without Saturn's final push, they wouldn't be where they are now. And without that rare planetary alignment in the late 1970s, the mission might not have happened at all. So when we talk about what Voyager detected at the edge of the solar system, it's worth remembering how it got there. Not through continuous propulsion, not through advanced engines, but through a series of precisely timed gravitational interactions that effectively turned the entire solar system into a launch system. No fuel could have done that, and now, decades later, those early decisions are still paying off, because the spacecraft are still moving, still sending data, and still heading into completely unknown territory. By the time both spacecraft passed Neptune in 1989, the original mission was effectively complete. Everything after that point was a bonus. No one in the 1970s expected these machines to still be working into the 21st century, let alone approaching 50 years in space. And yet, here we are. The reason comes down to a mix of engineering choices that, at the time, weren't about longevity, they were about reliability. But those same decisions ended up giving the Voyagers something rare, the ability to keep adapting long after their primary mission ended. The most important piece of that is power. Out near Jupiter or Saturn, solar panels already become inefficient. By the time you reach Neptune, sunlight is about 900 times weaker than it is at Earth. Solar power simply wasn't an option. So instead, both Voyager 1 and Voyager 2 were equipped with radioisotope thermoelectric generators, RTGs. These devices don't rely on sunlight at all. Inside them is plutonium-238, a radioactive material that naturally decays and releases heat. That heat is converted directly into electricity through solid-state components. There are no moving parts, which means there's very little that can mechanically fail. But there's a catch. The power output slowly decreases over time as the radioactive material decays. At launch, each Voyager had enough power to run all of its scientific instruments, communication systems, heaters, and onboard computers. But every year that power drops a little. Not suddenly, not unpredictably, just a steady decline. So engineers had to start making trade-offs. In the 1990s, they began turning off instruments that were no longer essential. Cameras were among the first to go because once the planetary flybys were complete, there was nothing left nearby to photograph. That saved power for instruments that could measure particles, magnetic fields, and plasma, things that were still relevant as the spacecraft moved farther out. Later, heaters were shut down. This was a risk. Many components on board were designed to operate within specific temperature ranges. Turning off heaters meant exposing them to extreme cold, far colder than what they were tested for on Earth. Some parts dropped to temperatures below -40 degrees Celsius, and yet they kept working. This is one of the most surprising parts of the Voyager story. Hardware that was never meant to operate under those conditions continued functioning anyway. Not perfectly, not without issues, but well enough to keep collecting data. Over time, engineers also found ways to reconfigure the spacecraft remotely. Each Voyager has multiple sets of thrusters used to keep its antenna pointed toward Earth. That alignment is critical. If the antenna drifts too far off target, communication is lost. Normally, these thrusters would wear out after years of use. But decades into the mission, when the primary thrusters started degrading, engineers did something unusual. They reactivated a backup set of thrusters that hadn't been used in decades. In the case of Voyager 1, these backup thrusters were originally intended for a different part of the mission and had been inactive since the early 1980s. Bringing them back online required careful planning because any mistake could have permanently damaged the spacecraft. It worked. That single decision extended the mission by years. Communication itself is another challenge that becomes harder over time. As the spacecraft move farther away, their signals spread out and weaken. By the time those signals reach Earth, they're incredibly faint, on the order of billionths of a watt. Detecting them requires some of the most sensitive radio equipment ever built. This is where NASA's Deep Space Network comes in, a global system of massive radio antennas located in California, Spain, and Australia. These stations work together to track and communicate with distant spacecraft, including the Voyagers. Even with that system, data rates are extremely low. At their current distance, the Voyagers transmit data at just a few hundred bits per second. That's thousands of times slower than a basic internet connection. Sending a single image would take hours, which is why imaging is no longer part of the mission. Instead, the focus is on transmitting small amounts of highly valuable scientific data, measurements of particles, fields, and waves that tell us what the environment is like out there. Time delay is another factor. Right now, Voyager 1 is so far away that it takes over 20 hours for a signal to travel one way. That means if engineers send a command, they won't know whether it worked until nearly 2 days later. There's no real-time control, no quick adjustments. Everything has to be planned carefully and executed with patience. Despite all of this, both spacecraft are still operating, but not without issues. In recent years, there have been moments where the data coming back didn't make sense, corrupted readings, unexpected telemetry, or signs that onboard systems weren't behaving normally. Each time, engineers had to diagnose the problem from billions of kilometers away, using limited information. Sometimes the fix involved rewriting parts of the spacecraft's software. Other times it meant rerouting data through backup systems that hadn't been used in decades. Every solution is a bit like solving a puzzle with missing pieces, and every successful fix extends the mission just a little longer. But there is a limit. The RTGs continue to lose power at a predictable rate, and eventually there won't be enough energy to run even the most essential systems. Instruments will be shut down one by one. Communication will become harder to maintain. At some point, likely in the early 2030s, the spacecraft will go silent. Not because they failed suddenly, but because they slowly ran out of the energy needed to keep going. Until then, engineers are doing everything they can to stretch out the remaining power, because every additional year means more data from a region of space we still don't fully understand. And that's the key reason the Voyagers matter today. They're not just old spacecraft still drifting through space. They are, right now, the only working probes sending back direct measurements from beyond the influence of the Sun. Everything we're learning about the boundary of the solar system and what lies beyond it is coming from machines that were designed before the internet existed. And somehow, they're still working. When people hear edge of the solar system, it sounds like there should be a clear boundary, a line you cross, and suddenly you're outside. But that's not how it works. There isn't a wall out there. There isn't even a sharp transition. What we call the edge is really a series of regions where the influence of the sun gradually weakens and starts competing with the environment between stars. To understand what Voyager 1 and Voyager 2 actually detected, you first need to understand what they were moving through. It starts with the solar wind. The sun isn't just sending out light and heat. It's constantly releasing a stream of charged particles, mostly electrons and protons, flowing outward in all directions. This stream is called the solar wind, and it moves at speeds of hundreds of kilometers per second. As it expands outward, it carries the sun's magnetic field with it. That creates a kind of bubble around the solar system known as the heliosphere. Inside this bubble, the sun dominates. The particles, the magnetic field, the overall environment, it's all shaped by solar activity. Planets orbit within this region, but they're not what defines it. The heliosphere extends far beyond Neptune, far beyond Pluto. For decades, this was considered the practical boundary of the solar system. But even the heliosphere isn't uniform. As the solar wind travels outward, it eventually starts to slow down. Not because it runs out of energy, but because it begins to push against something else, the interstellar medium. This is the material that exists between stars, extremely thin gas, mostly hydrogen, along with cosmic rays and magnetic fields that come from outside our solar system. At some point, the outward pressure of the solar wind and the inward pressure of the interstellar medium reach a balance. That's where things start to get complicated. The first major region the Voyagers encountered on their way out is called the termination shock. This is where the solar wind, which has been moving faster than the speed of sound in that environment, suddenly slows down to subsonic speeds. It's not a sharp shock like an explosion. It's more like a gradual but noticeable transition where particle behavior changes. Beyond that is a region called the heliosheath. Here the solar wind is slower, more turbulent and compressed. It's still dominated by the sun, but it's no longer behaving in a simple, steady way. Particles start interacting more with incoming material from interstellar space. Magnetic fields twist and fluctuate. This is a kind of buffer zone. And then, eventually, you reach what most scientists consider the true boundary, the heliopause. This is the point where the solar wind can no longer push outward effectively. Beyond this boundary, the interstellar medium dominates. The sun's influence doesn't disappear, but it becomes secondary. That's the key distinction. Crossing the heliopause doesn't mean you've left the solar system in every sense. The sun's gravity still extends much farther, and objects like comets in the Oort cloud are still loosely bound to it. But in terms of the space environment, the particles and fields, the heliopause marks the transition into interstellar space, and that's exactly what the Voyagers were heading toward. For a long time, scientists tried to predict where this boundary would be. Estimates varied widely. Some models suggested it might be around 100 astronomical units from the Sun, about 100 times the distance between Earth and the Sun. Others placed it farther out, but no one knew for sure, because no spacecraft had ever been there. That's what made the Voyagers so important. As they moved outward, they were sending back real measurements, data that could confirm or challenge existing models, and almost immediately things started to look more complicated than expected. The termination shock wasn't where some models predicted it would be. The heliosheath turned out to be more turbulent. Particle behavior didn't always match expectations. Even the idea of a smooth, layered structure started to break down. Instead of neat boundaries, the data suggested something messier. Regions that shift over time, influenced by solar activity, magnetic fields, and interactions with the interstellar medium. The edge wasn't fixed. It could move. Solar activity plays a big role in that. The sun goes through cycles roughly every 11 years, during which its activity increases and decreases. Stronger solar activity can push the heliosphere outward slightly. Weaker activity allows it to contract. So the distance to the heliopause isn't constant. That means when Voyager 1 crossed the heliopause in 2012 and Voyager 2 followed in 2018, they weren't crossing a fixed, permanent boundary. They were passing through a region that changes over time, and even then, the crossing wasn't as obvious as you might expect. There wasn't a sudden visual change, no dramatic shift you could see with a camera. Instead, it showed up in the data: a drop in solar particles, an increase in cosmic rays, changes in magnetic field measurements. You had to interpret the signals to understand what had happened, which is why, at first, there was some debate about whether Voyager 1 had actually crossed into interstellar space. It took time to analyze the data and confirm that yes, it had passed beyond the Sun's dominant influence. And even now, the exact definition of leaving the solar system depends on what you mean. If you're talking about gravitational influence, the boundary is much farther out, in the distant Oort cloud. The Voyagers won't reach that region for tens of thousands of years, but if you're talking about the space environment, the particles and magnetic fields that define the local conditions, then the heliopause is the line that matters. That's the boundary the Voyagers crossed. And beyond it, they started measuring something completely different. Not empty space, but a new kind of space, one shaped not by our Sun, but by the galaxy itself. Long before reaching interstellar space, both Voyagers hit something that scientists had only modelled on paper, the termination shock. Up to that point, the solar wind had been moving outward from the Sun at supersonic speeds. That matters because when something travels faster than the speed at which disturbances can move through a medium, information can't propagate ahead of it. Everything stays smooth until it doesn't. At some distance from the Sun, the solar wind starts feeling resistance from the interstellar medium. It's subtle at first, but eventually it builds up enough that the flow can't stay supersonic anymore. That's where the termination shock forms. When Voyager 1 crossed this region in late 2004, it didn't hit a clean, single boundary. Instead, the spacecraft detected a series of changes that pointed to a more complex structure. The speed of the solar wind dropped. Energetic particles behaved differently. Magnetic field measurements became more chaotic. It was clear something fundamental had changed, but it wasn't happening in a neat, predictable way. Then Voyager 2 reached the termination shock in 2007, and things got even more interesting. It crossed the boundary at a completely different distance from the Sun compared to Voyager 1. That wasn't supposed to happen. If the heliosphere was symmetrical, both spacecraft should have encountered the termination shock at roughly the same distance. Instead, Voyager 2 hit it closer in. That suggested the entire structure of the heliosphere was being distorted, most likely by the pressure and magnetic fields of the interstellar medium pushing unevenly against it. In other words, the solar system's outer boundary isn't a perfect bubble. It's compressed on one side and stretched on another. That was the first major surprise. But the second surprise came from what the termination shock actually looked like in the data. Scientists expected a relatively sharp transition, a clear before and after signal. Instead, both spacecraft detected something more irregular. The boundary seemed to fluctuate. At times, it looked like the spacecraft might have crossed it multiple times, as if the shock itself was moving back and forth. This suggested that the region wasn't stable. It could shift depending on solar activity, changes in the solar wind, or external pressure from interstellar space. And then there were the particles. One of the key instruments on board both Voyagers measures energetic charged particles, basically tracking how many high-energy ions are moving through space and how they behave. At the termination shock, scientists expected to see a certain kind of acceleration process, where particles gain energy as they bounce across the shock boundary. This is similar to what happens in other astrophysical shocks, like those from supernova remnants. But the data didn't fully match those expectations. Instead of seeing the predicted distribution of energetic particles, the Voyagers detected something different. The acceleration mechanism seemed less efficient than expected, or at least more complicated. Some particles were gaining energy in ways that didn't fit existing models. This forced scientists to rethink how shocks work in space, not just here, but across the universe. Because termination shocks aren't unique to our solar system. Similar processes happen around other stars, in stellar winds, and in much more extreme environments. What Voyager observed provided a real-world data point that could be applied far beyond our local region. Then there was the turbulence. Beyond the termination shock lies the heliosheath, and this is where the solar wind slows down and becomes more chaotic. Voyager data showed that this region isn't smooth at all. It's filled with fluctuations in particle density, magnetic field strength, and flow direction. Imagine a river that suddenly slows down and starts swirling, forming eddies and unpredictable currents. That's a rough analogy for what's happening in the heliosheath, and the Voyagers were right in the middle of it. Another unexpected detail came from temperature measurements, When a flow slows down from supersonic to subsonic speeds, you'd normally expect a significant increase in temperature. That's a standard result in fluid dynamics, but the temperatures measured by Voyager didn't match predictions. They were lower than expected. This suggested that some of the energy wasn't going into heating the plasma. Instead, it might have been going into accelerating particles or interacting with magnetic fields in ways that weren't fully understood. Again, models had to be updated. One more subtle but important observation involved the direction of particle flow. Before the termination shock, the solar wind moves mostly outward, away from the Sun. After crossing into the heliosheath, the flow becomes less directional. Voyager detected particles moving in more varied directions, indicating a loss of the simple radial structure that dominates closer to the Sun. That's another sign that the Sun's influence is weakening, but not gone, because even in the heliosheath, the solar wind is still present. It's just slower, more compressed, and interacting more strongly with incoming material from interstellar space. This region turned out to be much thicker than some models predicted. Voyager 1 spent about 8 years traveling through the heliosheath before reaching the heliopause. Voyager 2 took a bit less time, but still several years. That's not a thin boundary. It's a vast, extended region with its own complex behavior. And throughout that entire journey, both spacecraft kept sending back data. Piece by piece, they built up a picture of what happens when the influence of a star starts to fade and collide with the environment of the galaxy. By the time they reached the outer edge of the heliosheath, one thing was clear. The boundary of the solar system isn't just a line. It's a dynamic, shifting region full of interactions that we're only beginning to understand. And just beyond it, something completely different was waiting. After years of moving through the chaotic heliosheath, both Voyagers approached the most important transition of the entire mission, the heliopause. This is the point where the solar wind effectively stops dominating. Beyond it, the environment is no longer controlled by the Sun, but by the interstellar medium, the material that fills the space between stars. For decades, this boundary was theoretical. Scientists had models, estimates, and indirect evidence, but no direct measurement. That changed in August 2012. That's when Voyager 1 started sending back data that didn't match anything it had seen before. At first, the change wasn't obvious. There wasn't a single moment where everything flipped. Instead, it showed up as a pattern across multiple instruments. One of the clearest signals came from particle detectors. Inside the heliosphere, the spacecraft had been measuring a steady flow of charged particles coming from the Sun, what we call the solar wind. But around mid-2012, those solar particles dropped sharply. At the same time, something else increased. Cosmic rays, high-energy particles coming from outside the solar system, suddenly became much more intense. Not gradually, but in a noticeable spike. It was as if a barrier had been crossed, and now the spacecraft was exposed to a different environment. That combination, a drop in solar particles and a rise in cosmic rays, was one of the strongest indicators that Voyager 1 had moved beyond the Sun's protective bubble. But there was a complication. Scientists expected that crossing the heliopause would also involve a significant change in the magnetic field direction. Inside the heliosphere, the magnetic field is shaped by the Sun. Outside, it should reflect the broader galactic field. But Voyager 1 didn't see a dramatic shift. The magnetic field's strength increased, which made sense, but its direction remained surprisingly similar to what it had been before the crossing. That led to uncertainty. Had Voyager 1 really entered interstellar space, or was it still inside some transitional region that hadn't been fully predicted? It took months of analysis to sort this out. Eventually, scientists concluded that Voyager 1 had indeed crossed the heliopause. The lack of a strong magnetic direction change suggested that the interstellar magnetic field in that region is aligned in a way that blends more smoothly with the solar field than expected. In other words, the boundary wasn't as clean as the models predicted. Then, in November 2018, Voyager 2 reached the same milestone. This time, the crossing was clearer. Voyager 2 had a fully functioning plasma instrument, unlike Voyager 1, whose plasma sensor had stopped working decades earlier. That meant it could directly measure the speed and density of the surrounding plasma. When Voyager 2 crossed the heliopause, it detected a sharp drop in the speed of solar wind particles, essentially going to zero. At the same time, the density of the surrounding plasma increased, consistent with interstellar space. That removed much of the ambiguity. Now there were two independent spacecraft on different paths, both confirming the same boundary. But even with that confirmation, the details were surprising. The heliopause isn't a simple, smooth surface. Data from both Voyagers suggests it's structured and possibly layered, with small-scale variations in density and magnetic fields. There are signs that the boundary can ripple or shift, influenced by changes in solar activity or conditions in the interstellar medium. It's more like a dynamic interface than a fixed shell. Another interesting detail is how thin the transition region appears to be. While the heliosheath stretches over billions of kilometers, the actual crossing of the heliopause seems to happen over a relatively short distance, on the order of days or weeks of travel time for the spacecraft. That suggests a fairly sharp transition in terms of particle populations, even if the underlying structure is complex. Then there's the question of pressure balance. The heliopause exists because the outward pressure of the solar wind is balanced by the inward pressure of the interstellar medium. But that balance isn't static. If solar activity increases, the heliosphere can expand slightly. If it decreases, the heliosphere can contract. That means the heliopause itself can move. It's not fixed in space. So when Voyager 1 crossed it at about 121 astronomical units from the Sun, and Voyager 2 crossed at around 119 astronomical units, those distances weren't permanent markers. They were snapshots in time, influenced by the conditions at that moment. Beyond the heliopause, both spacecraft entered what we now call interstellar space. But that doesn't mean they're completely free of the Sun's influence. The Sun's gravity still extends much farther out. In fact, it dominates out to distances tens of thousands of astronomical units away, in a region known as the Oort cloud. The Voyagers won't reach that region for a very long time, so in a gravitational sense, they're still inside the solar system. But in terms of the environment, the particles, the magnetic fields, the plasma, they are now in a different regime. And that's what matters for understanding the boundary between star systems, because for the first time we have direct measurements from both sides of that boundary. We can compare what space looks like when it's dominated by our Sun versus when it's shaped by the galaxy. And what we've learned is that the transition isn't clean, isn't simple, and doesn't behave exactly the way we expected. Which is exactly why these measurements are so valuable, because they replace assumptions with data. And just beyond that boundary, the Voyagers started detecting something even more unusual, signals that revealed the structure of interstellar space itself in a way no one had ever measured before. Once both spacecraft crossed the heliopause, something subtle but incredibly important showed up in the data, signals that, at first glance, didn't look like much. No images, no dramatic spikes, just faint oscillations. But those oscillations turned out to be one of the most direct ways we've ever measured what interstellar space is actually like. Out there, space isn't completely empty. It's filled with a very thin plasma, ionized gas made of charged particles. And like any plasma, it can support waves. These are called plasma oscillations. The idea is simple. If you disturb a cloud of charged particles, the electrons and ions don't just settle back into place immediately. They oscillate, creating waves that move through the plasma. The frequency of those waves depends on how dense the plasma is. So if you can measure the frequency, you can figure out the density of the space around you. That's exactly what Voyager 1 started detecting after crossing into interstellar space. But there's a catch. The spacecraft doesn't hear these waves the way we hear sound. There's no air out there, so sound as we know it can't travel. Instead, Voyager measures the electrical signals associated with these oscillations. Scientists then convert those signals into audio frequencies so we can interpret them. That's where the idea of a cosmic hum comes from. What Voyager detected wasn't a one-time event. It was a series of plasma wave detections over several years, often triggered by shock waves from solar eruptions that had traveled all the way out to interstellar space. When a powerful burst of solar activity occurs, like a coronal mass ejection, it sends a wave of energy outward through the heliosphere. Even after crossing the heliopause, those disturbances can continue traveling and eventually interact with the interstellar plasma. When that happens, they excite oscillations. Voyager picks them up. By analyzing these signals, scientists were able to calculate the density of interstellar plasma around the spacecraft. And the results were surprising. The density was higher than expected. Before Voyager, estimates of interstellar Plasma density in our region of the galaxy were based mostly on indirect observations. But the measurements from Voyager showed that the local interstellar medium is denser than many models predicted, roughly about 40 times denser than the plasma inside the heliosphere. That's a big difference, and it has implications for how the heliosphere forms and behaves. A denser interstellar medium means more pressure pushing inward against the solar wind, which helps explain why the heliosphere is shaped the way it is. But there's more. The pattern of these plasma waves also revealed that interstellar space isn't uniform. The density can vary over time and distance. There are regions where it's slightly denser or more rarefied, and those variations affect how waves propagate. In some cases, Voyager detected gradual changes in plasma density over periods of months or years. That suggests the spacecraft is moving through regions with different properties, not dramatically different, but enough to be measurable. This is important because it gives us a direct probe of the local interstellar environment. Before this, most of what we knew about interstellar space came from observations of distant stars, how their light is absorbed or scattered by intervening material. That gives you an average picture over huge distances. Voyager, on the other hand, is giving us a point-by-point measurement. It's like the difference between looking at a landscape from space and walking through it. Another interesting detail is how these plasma waves help confirm that Voyager is truly in interstellar space. Inside the heliosphere, plasma densities are much lower. The frequencies of plasma oscillations are correspondingly lower. After crossing the heliopause, the frequencies detected by Voyager increased in a way that matches the higher density of interstellar plasma. That's another independent line of evidence that the spacecraft is no longer in a solar-dominated environment. And then there's the timing. Some of the strongest plasma wave signals detected by Voyager 1 occurred years after it crossed the heliopause. That's because the disturbances that triggered them, solar eruptions, take a long time to travel that far. We're talking about events that happened at the Sun, then propagated outward for years before finally interacting with the interstellar medium near the spacecraft. So in a way, Voyager is still detecting the delayed effects of solar activity, even after leaving the heliosphere. But the environment those disturbances are moving through is now fundamentally different. That's what makes these measurements so valuable. They're not just telling us about interstellar space in isolation. They're showing us how solar activity interacts with that environment across vast distances and timescales. And all of this comes from signals that, at first glance, look almost insignificant. Tiny oscillations in a nearly empty medium. But when you decode them, they reveal something much bigger: the structure, density, and behavior of the space between stars. And that's something we had never measured directly before, because until Voyager, no spacecraft had ever been there. One of the biggest expectations before the Voyagers reached the heliopause had to do with magnetic fields. Inside the heliosphere, the magnetic field is shaped by the Sun. As the Sun rotates, it drags its magnetic field outward with the solar wind, twisting it into a spiral pattern known as the Parker spiral. That structure dominates everything inside the solar bubble. Outside the heliopause, that influence should fade. So the assumption was straightforward. Once a spacecraft crossed into interstellar space, it should detect a magnetic field that looks completely different, one shaped by the galaxy instead of the Sun. But that's not what happened. When Voyager 1 crossed the heliopause in 2012, its magnetometer recorded an increase in magnetic field strength. That part made sense. The interstellar medium was expected to have a stronger, more stable magnetic field than the turbulent solar wind near the boundary. The surprise was the direction. Instead of seeing a sharp change, the magnetic field direction stayed almost aligned with what Voyager had been measuring inside the heliosphere. Not identical, but close enough that it didn't match predictions. That created a problem. If Voyager had truly crossed into interstellar space, why didn't the magnetic field shift the way models said it should? At first, this led to real uncertainty. Some scientists wondered if Voyager 1 might still be inside a previously unknown outer layer of the heliosphere, a region where solar and interstellar fields were somehow blending. But over time, as more data came in, a different explanation started to make more sense. The interstellar magnetic field in our local region of the galaxy appears to be oriented in a way that's not drastically different from the Sun's magnetic field at the boundary. Instead of a sharp angle between the two, there's a kind of gradual alignment. That means when Voyager crossed the heliopause, it didn't move from one clearly distinct magnetic environment into another. It moved into a region where the two fields are already somewhat aligned, so the transition looked smoother than expected. Then came Voyager 2 in 2018. Its data confirmed the same general pattern. Again, there was an increase in magnetic field strength at the heliopause. Again, the direction didn't change dramatically. That consistency between two spacecraft on different trajectories strengthened the conclusion that this wasn't a fluke. It was a real feature of how our solar system interacts with the galaxy. But the details go deeper than just alignment. The data also showed that the magnetic field just beyond the heliopause is less turbulent than in the heliosheath. Inside the boundary region, the solar wind creates fluctuations and irregularities in the magnetic field. Once you move into interstellar space, those fluctuations decrease. The field becomes smoother, not perfectly uniform, but more stable over time. That tells us something about the environment beyond the sun's influence. It's not completely chaotic. There's structure to it, large-scale magnetic fields that extend across vast regions of space. And those fields play a role in shaping the heliosphere itself. Remember earlier when we talked about how the heliosphere isn't perfectly spherical? The interstellar magnetic field is one of the main reasons why. It exerts pressure on the solar wind, compressing the heliosphere in some directions and allowing it to extend further in others. So by measuring the magnetic field outside the heliopause, the Voyagers are helping us understand the shape of our entire solar bubble. Another interesting detail is how the magnetic field interacts with charged particles. In space, particles don't just move freely in straight lines. They tend to spiral along magnetic field lines. That means the structure of the magnetic field influences how particles travel, whether they get trapped, deflected, or allowed to pass through. This is especially important when it comes to cosmic rays. The heliosphere acts as a kind of shield, partially blocking high-energy particles from outside the solar system. The effectiveness of that shield depends in part on how magnetic fields are arranged at the boundary. Voyager data suggests that the transition isn't a simple barrier. Instead, there may be regions where particles can more easily leak through, guided by the alignment of magnetic fields. That could explain why the increase in cosmic rays beyond the heliopause is sharp, but not infinite. Some particles are still influenced by the structure of the boundary, and then there's the question of reconnection. Magnetic fields can break and reconnect under certain conditions, releasing energy and changing the way particles move. This process, known as magnetic reconnection, is common in space plasmas. There's evidence that reconnection might be happening near the heliopause where solar and interstellar magnetic fields interact. If that's the case, it could create pathways for particles to cross the boundary more easily. That's still an active area of research. What's clear is that the magnetic environment at the edge of the solar system is more complex than a simple inside versus outside distinction. It's not just solar field on one side and galactic field on the other. It's an interaction zone where the two influence each other, and the Voyagers are the only instruments we have that are directly measuring that interaction. Every data point they send back adds to a picture that we couldn't have built any other way, because you can't simulate this perfectly in a lab. You can't observe it directly from Earth. You need something out there, in that environment, taking measurements in real time. That's exactly what the Voyagers are doing, and what they're showing is that even something as seemingly straightforward as a magnetic boundary turns out to be layered, dynamic, and full of unexpected behavior. Which raises a bigger question. If the boundary itself is this complex, what does that mean for everything beyond it? One of the clearest signs that the Voyagers had reached a completely different region of space didn't come from magnetic fields or plasma waves, it came from radiation. Long before crossing the heliopause, both Voyager 1 and Voyager 2 were already detecting cosmic rays, high-energy particles moving through space at nearly the speed of light. These particles come from outside the solar system, many of them originating from extreme events like supernova explosions. But inside the heliosphere, those cosmic rays are partially blocked. The solar wind, combined with the sun's magnetic field, acts like a shield. It doesn't stop all incoming radiation, but it reduces the intensity. It slows some particles down, deflects others, and creates a kind of protective bubble around the solar system. That's one of the reasons Earth isn't constantly exposed to the full intensity of galactic radiation. But as the Voyagers moved outward, that shielding effect started to weaken. And when they crossed the heliopause, the change was immediate and obvious. The number of detected cosmic rays jumped sharply. For Voyager 1, this happened in 2012. Instruments on board recorded a sudden increase in high-energy particles, far more than what had been measured just inside the heliosphere. At the same time, the intensity of lower-energy particles from the Sun dropped off. It was a clean swap. Less solar influence, more galactic influence. Voyager 2 saw the same pattern in 2018, confirming that this wasn't a one-time anomaly. 2 spacecraft, 2 different paths, same result. That consistency is important because it tells us this is a fundamental feature of the boundary, not something unique to one location. But the details matter. The increase in cosmic rays wasn't gradual. It wasn't a slow ramp-up over millions of kilometers. It happened over a relatively short distance, suggesting that the heliopause acts as a fairly effective barrier. Not perfect, but strong. This tells us something critical about how the heliosphere works. It's not just a passive bubble. It actively reduces the amount of high-energy radiation that reaches the inner solar system. And that has real consequences. For one, it affects the radiation environment for planets, including Earth. While Earth has its own magnetic field and atmosphere that provide additional protection, the heliosphere is the first line of defense. Without it, the baseline level of cosmic radiation in the inner solar system would be significantly higher. That's not just a technical detail, it matters for things like long-term space travel, satellite electronics, and even atmospheric chemistry. Voyager's measurements give us a direct way to quantify that difference. Another interesting point is the energy range of the detected particles. Cosmic rays cover a wide spectrum of energies. Some are relatively low energy and easier to deflect. Others are extremely energetic and can pass through magnetic fields more easily. Voyager data shows that the heliosphere is more effective at blocking lower energy cosmic rays, while higher energy ones can penetrate more deeply. That means the radiation environment changes not just in intensity, but in composition. Beyond the heliopause, the mix of particles shifts toward higher energies overall. That has implications for how we think about interstellar space. It's not just more radiation, it's a different kind of radiation environment, one dominated by particles that have traveled across the galaxy carrying information about distant events. In a way, cosmic rays are messengers. They tell us about processes happening far beyond our solar system, supernova remnants, stellar winds from other stars, possibly even more exotic sources. By measuring them directly, the Voyagers are giving us a local sample of that broader galactic activity. There's also a timing aspect to consider. The intensity of cosmic rays isn't constant over time, it's influenced by solar activity. During periods of high solar activity, the heliosphere becomes more turbulent and better at deflecting incoming particles, which reduces cosmic ray intensity inside the solar system. During quieter periods, more cosmic rays get through, but beyond the heliopause, that modulation effect drops off significantly. Voyager's data shows a more stable cosmic ray environment, less influenced by the Sun's cycles. That's another confirmation that the spacecraft are no longer inside the Sun's protective bubble. And then there's the boundary itself. The sharp increase in cosmic rays at the heliopause suggests that the transition region is relatively thin in terms of particle behavior. It doesn't take a vast distance for the shielding effect to drop off. Once you cross that line, the environment changes quickly. That's important for modeling how particles move across the boundary. It suggests that the heliopause acts more like a filter than a gradual gradient. Certain particles are blocked or deflected, while others pass through depending on their energy and the structure of the magnetic field. Understanding that filtering process is still an active area of research, because it doesn't just apply here. Every star with a stellar wind likely creates its own version of a heliosphere, an astrosphere, and each of those will interact with the surrounding interstellar medium in similar ways. So by studying our own boundary, we're learning something more general about how stars shape their environments. And the Voyagers are the only tools we have that are directly measuring that process from the outside. Right now, still sending data, still detecting particles that have traveled across the galaxy before finally being recorded by instruments built in the 1970s. That alone is remarkable. But it also sets up the next question. If the radiation environment changes this much at the boundary, what about the temperature? When people think about space, especially the space between stars, the assumption is usually the same. It must be extremely cold. And in one sense, that's true. If you are out there far beyond the heliopause, You wouldn't feel heat the way you do on Earth. There's almost nothing to transfer that heat to you. No air, no dense material, just a very thin plasma. But when Voyager 1 and Voyager 2 started measuring the temperature of that plasma, the numbers didn't match that expectation at all. They were surprisingly high. Not warm in a human sense, but physically energetic. This comes down to how temperature is defined in space. On Earth, temperature is something we feel because particles, molecules in the air, are constantly colliding with our skin. The faster those particles move, the hotter it feels. That's because temperature, at a basic level, is a measure of the average kinetic energy of particles. In interstellar space, the particles are moving fast enough to correspond to temperatures of tens of thousands of degrees Celsius. That sounds extreme. But here's the key detail. The density is incredibly low. There are only a few particles per cubic centimeter out there. That means even though each particle carries a lot of energy, there aren't enough of them to transfer that energy efficiently. So if you were somehow floating in that environment, you wouldn't feel hot, you'd feel cold because there's almost no heat transfer. So when scientists talk about high temperatures in interstellar space, they're talking about particle energy, not heat in the everyday sense. That distinction matters. Voyager's instruments don't measure temperature directly the way a thermometer does. Instead, they measure properties like particle speeds, densities, and energy distributions. From that, scientists calculate what's known as the plasma temperature. And what they found beyond the heliopause was that the interstellar medium is hotter than expected. Inside the heliosphere, especially in the heliosheath, temperatures can be elevated due to the slowing and compression of the solar wind. But once you move beyond that region, models predicted a certain range of temperatures for the local interstellar medium. Voyager's data suggested values that were higher. This raised a question. Where is that extra energy coming from? One possibility is that the interstellar medium in our region of the galaxy has been heated by past events. Like shockwaves from nearby supernova explosions, those events can send energy through space over long distances, raising the kinetic energy of particles even in relatively quiet regions. Another factor could be the interaction at the heliopause itself. As the solar wind pushes outward and meets the interstellar medium, energy is exchanged. Some of that energy could be transferred into particle motion on the interstellar side, effectively heating the plasma locally. There's also the role of magnetic fields. Charged particles don't just move randomly, they spiral along magnetic field lines, and under certain conditions, those fields can transfer energy to the particles. This can lead to heating mechanisms that aren't as straightforward as simple collisions. Voyager's measurements don't give a complete answer, but they provide constraints, real data that models have to match. And so far, those models are still being refined. Another interesting detail is how temperature varies across the boundary. The transition from the heliosheath to interstellar space isn't just a shift in particle origin, it's also a shift in how energy is distributed. Inside the heliosphere, energy comes primarily from the Sun. Outside, it reflects a broader mix of galactic processes. That means the temperature profile isn't smooth. There can be gradients, variations, and localized changes depending on conditions. Voyager has detected some of these variations over time, suggesting that even interstellar space has structure at smaller scales than we once thought. Again, not dramatic structure, nothing like planets or clouds, but measurable differences in density and energy. And that's important, because it tells us that the space between stars isn't just a uniform background. It has its own dynamics influenced by events happening across the galaxy. There's also a practical implication. Understanding the temperature and energy of interstellar plasma matters for any future mission that might try to travel through it. High-energy particles can affect spacecraft materials, electronics, and shielding requirements. Voyager gives us a first look at what that environment is actually like, not in theory, but in reality. And the takeaway is clear. Interstellar space is not empty, not uniform, and not as simple as cold and quiet. It's a low-density, high-energy environment shaped by processes that operate on scales far beyond our solar system. And the Voyagers are moving through it right now, measuring it directly. Which leads to a bigger picture. If the environment out there is this complex, what does that say about the overall shape of the region our Sun has carved out in space? For a long time, the default mental picture of the solar system's boundary was simple: a big, round bubble centered on the Sun. It made sense. The sun sends out the solar wind in all directions, so you'd expect that wind to inflate a roughly spherical region, the heliosphere, pushing outward evenly until it meets the interstellar medium. But once data started coming in from Voyager 1 and Voyager 2, that picture didn't hold up. The first clue was the termination shock crossings. Voyager 1 crossed it in 2004. Voyager 2 crossed it in 2007. But they didn't cross at the same distance from the sun. Voyager 2 encountered it closer in. That difference wasn't small enough to ignore. It meant the heliosphere isn't symmetrical. Something is pushing on it unevenly. The most likely cause is the interstellar medium, the gas and magnetic fields surrounding our solar system. The sun is moving through the galaxy, and as it does, it experiences a kind of headwind from that medium. That pressure compresses the heliosphere on one side and stretches it out on the other. So instead of a sphere, you get something more like a distorted bubble. But even that might be too simple. Over the past decade, scientists have proposed different models to explain the shape of the heliosphere. One of the more interesting ones suggests it might look less like a comet with a long tail and more like a croissant. Not literally, of course, but the idea is that instead of a single extended tail trailing behind the sun, the heliosphere might have two lobes, shaped by the way the solar magnetic field interacts with the interstellar magnetic field. In this model, the sun's magnetic field helps confine the solar wind into these two structures, rather than allowing it to stretch into one long tail. Voyager data doesn't give a complete map of this shape. There are only two spacecraft, and they're moving in specific directions. But the differences between their measurements support the idea that the heliosphere has a more complex geometry than a simple sphere. Other missions have added to this picture. For example, NASA's IBEX mission, Interstellar Boundary Explorer, has mapped energetic neutral atoms coming from the boundary region. Those observations revealed a strange ribbon-like structure in the sky, an unexpected feature that seems to trace where the interstellar magnetic field is interacting with the heliosphere. That's another piece of evidence that magnetic fields are playing a major role in shaping the boundary. So what does the heliosphere actually look like? The honest answer is, we don't have a complete picture yet. We have models, we have indirect observations, and we have direct measurements from the Voyagers along two paths. But we don't have a full 3D map. It's a bit like trying to figure out the shape of a cloud by flying two drones through it along different routes. You get valuable data, but you're still missing the full structure. What we do know is that the heliosphere is dynamic. It changes over time. Solar activity affects how strongly the solar wind pushes outward. The interstellar medium can vary as the sun moves through different regions of the galaxy. Magnetic fields can shift and interact in ways that alter the shape. So even if we could map it perfectly today, that map wouldn't stay accurate forever. And that has bigger implications, because every star with a stellar wind creates its own version of a heliosphere, what scientists call an astrosphere. The shape of that astrosphere depends on the star's activity, its magnetic field, and the properties of the surrounding interstellar medium. So by studying our own heliosphere, we're learning something more general about how stars interact with their environments. Voyager's role in this is critical. Without those direct measurements, crossings at different distances, variations in particle behavior, changes in magnetic fields, we wouldn't have the evidence needed to challenge the simple spherical model. We'd still be relying mostly on theory. Instead, we now know that the boundary of our solar system is shaped by a combination of forces: the outward pressure of the solar wind, the inward pressure of the interstellar medium, the structure of magnetic fields on both sides, and those forces don't balance evenly. That's why the heliosphere looks the way it does, distorted, dynamic, and still not fully understood. It's also why the exact distances where Voyager 1 and Voyager 2 crossed the heliopause were different. They weren't hitting a perfect shell, they were passing through different parts of a complex structure. And that complexity is exactly what makes the data so valuable, because every unexpected detail forces us to refine our models. Every mismatch between prediction and observation reveals something new about how our solar system fits into the galaxy. And right now, the Voyagers are still moving outward, still sampling that structure from the inside out, which brings up something almost easy to forget. These spacecraft aren't just scientific instruments, they're also carrying something else. There's a part of the Voyager mission that has nothing to do with plasma, magnetic fields, or cosmic rays. It's something much simpler and, in a way, much stranger. Both Voyager 1 and Voyager 2 are carrying a physical object attached to their sides. The Voyager Golden Record. It's not a data drive, not a radio transmitter. It's an actual 12-inch gold-plated copper disc, designed to be played like a vinyl record. The idea wasn't scientific in the usual sense. It was symbolic, but still carefully thought through. In the mid-1970s, as the Voyager mission was being prepared, a small team led by Carl Sagan was asked to create a kind of time capsule, something that could represent Earth and humanity in case the spacecraft were ever encountered by another civilization. That's a big if. The distances involved are enormous. Even moving at tens of thousands of kilometers per hour, the Voyagers will take tens of thousands of years just to pass near another star. The chances of them being found are extremely small. But the idea wasn't really about probability, it was about making a record anyway. So, what do you put on something like that? The team had to decide how to represent an entire planet, its life, its cultures, its sounds, in a format that could potentially be understood by beings with no shared language. They started with images. The record contains 116 encoded pictures, covering a wide range of subjects: human anatomy, mathematical definitions, basic scientific concepts, landscapes, animals, and everyday scenes from life on Earth. There are images of cities, of people eating, of different cultures and environments. The goal was to show both the biological and technological aspects of life here. Then there are sounds. Not music at first, just raw audio. Things like wind, rain, thunder, ocean waves, animal calls, footsteps, a heartbeat, the sounds of a rocket launch. The idea was to capture the natural and mechanical environment of Earth in a way that doesn't depend on language. After that comes music. The selection is deliberately broad. It includes classical pieces from composers like Bach and Beethoven, but also traditional music from different parts of the world: India, China, Africa, the Middle East. There's even a recording of Chuck Berry's Johnny B. Good. The point wasn't to define the best music, but to show diversity. And then there are the greetings. Short-spoken messages in 55 different languages, ranging from widely spoken ones like English and Spanish to less common languages. There's also a message from the Secretary-General of the United Nations at the time and one from the President of the United States. All of it is encoded in analog form, along with instructions etched onto the record's cover on how to play it. Those instructions use basic physics and mathematics, referencing things like the hydrogen atom's properties to establish units of time and measurement. It's an attempt to create a universal starting point. Not perfect, not guaranteed to be understood, but grounded in concepts that should be recognizable anywhere in the universe. What makes the Golden Record interesting isn't just what's on it, it's what it represents. It's a snapshot of humanity in the 1970s. Not complete, not fully representative, but intentional. Every image and sound was selected, debated, and included for a reason. And now it's out there. Both Voyagers are on escape trajectories. They won't return, they won't orbit another star, they'll just keep moving through the galaxy, carrying those records with them. Over time, the spacecraft will stop transmitting. Their instruments will go silent as power runs out. But the physical structure of the spacecraft and the records attached to them will remain. Space is mostly empty, which means there's very little to erode or damage them. Micrometeoroid impacts are possible, but over long timescales, much of the spacecraft could remain intact. In tens of thousands of years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445. Voyager 2 will have its own distant encounters. But even then, the chances of interception are extremely low. So the Golden Record is less about communication and more about presence. It's a way of saying, this existed. At a specific moment in time, on a small planet orbiting an ordinary star, a species developed the ability to send objects beyond its own system, and chose to include a record of itself. That's the context. And it sits alongside all the scientific instruments, quietly travelling outward. Still attached, still intact. While the Voyagers continue measuring particles and fields, sending back data from beyond the heliopause, they're also carrying this completely different kind of payload. One that doesn't transmit, one that doesn't update, just a fixed message moving through interstellar space. And while that part of the mission doesn't change over time, everything else does, especially the challenge of staying in contact with spacecraft that are now more than 20 billion kilometers away. Right now, both Voyager 1 and Voyager 2 are so far from Earth that distance stops being intuitive. We're not talking millions of kilometers, not even billions in the way we usually think about planetary distances. Voyager 1 is over 20 billion kilometers away. Voyager 2 isn't far behind. At that scale, even light, the fastest thing in the universe, takes a long time to travel. A signal from Voyager 1 takes more than 20 hours just to reach Earth. That's one way. So if engineers send a command, they have to wait nearly 2 full days to know whether it worked. There's no joystick control, no real-time correction. Everything has to be calculated, tested, and sent with the assumption that you won't get immediate feedback. That alone makes communication difficult. But the bigger challenge is signal strength. The Voyagers transmit using a radio signal that was already modest in power when they launched in the 1970s. Over these enormous distances, that signal spreads out in all directions. By the time it reaches Earth, it's incredibly faint, on the order of a billionth of a watt. That's less power than what a typical electronic device uses in a fraction of a second, and yet we can still detect it. This is where NASA's Deep Space Network comes in. It's a global system of giant radio antennas with major facilities in California, Spain, and Australia. Each site has massive dish antennas, up to 70 meters in diameter, designed to pick up extremely weak signals from deep space. The 3 locations are spaced around the Earth so that at least one of them can maintain contact with a spacecraft at any given time as the planet rotates. Without this network, the Voyagers would have gone silent decades ago. Even with it, communication isn't easy. The data rate is extremely low, just a few hundred bits per second. That's thousands of times slower than even the most basic internet connection. You couldn't stream anything. You couldn't send images efficiently, which is why the mission doesn't try to. Instead, the spacecraft send back small packets of scientific data, measurements of particle counts, magnetic field strength, plasma waves. Each bit is valuable, so the system is designed to prioritize reliability over speed. There's also error correction built into the communication process. Because the signal is so weak, it's susceptible to interference and noise. To deal with that, the data is encoded in a way that allows errors to be detected and corrected when the signal is received on Earth. That means even if part of the signal is lost or distorted, the original data can often be reconstructed. Another challenge is pointing accuracy. The Voyagers use a high-gain antenna, a large dish that focuses their radio signal into a narrow beam aimed at Earth. But as the spacecraft travel farther away, that beam covers a smaller and smaller angle relative to the distance. That means the antenna has to be pointed very precisely. Even a small drift could cause the signal to miss Earth entirely. To maintain that alignment, the spacecraft use small thrusters to adjust their orientation. These thrusters fire in tiny bursts, just enough to keep the antenna locked onto our planet. Over decades, those adjustments add up. Fuel is limited, and the thrusters themselves wear out over time. As mentioned earlier, engineers have had to switch to backup thrusters in some cases, systems that hadn't been used in decades. Every adjustment is carefully calculated because there's no room for trial and error at this distance. Then there's the issue of timing. Because of the long signal delay, communication operates on a schedule. Commands are prepared in advance, uploaded during a specific window, and then executed by the spacecraft at a predetermined time. The spacecraft themselves also store data temporarily before transmitting it, since they can't send everything continuously. It's a slow, methodical process. And it has to be. Because once the signal is sent, there's no taking it back. Despite all these challenges, communication has continued for nearly 5 decades. But it's getting harder. As the RTGs lose power, there's less energy available for the transmitter. That means the signal could become even weaker over time. At some point, it may fall below the threshold that the Deep Space Network can reliably detect. When that happens, contact will be lost. Not suddenly, but gradually. Signals will become harder to decode. Data rates may drop further. Eventually, the spacecraft won't be able to transmit at all. Until then, engineers are doing everything they can to keep the link alive. They adjust transmission power, they optimize antenna alignment, they schedule communication windows carefully to make the most of available resources. Because every successful transmission adds another piece to the puzzle. Another data point from interstellar space. And it's worth remembering how unusual this is. These spacecraft were designed in an era before modern computing, before digital communication as we know it today. And yet, they're still maintaining contact across distances that were barely imaginable at the time. That's not just a testament to engineering, it's a reminder of how far careful design and long-term planning can go. Because right now, at the edge of interstellar space, we still have a working connection. And through that connection, the Voyagers are still telling us what's out there. But that connection won't last forever. At some point, both Voyager 1 and Voyager 2 will stop sending data. Not because they suddenly fail, not because they hit something, but because they slowly run out of power. From the very beginning, the mission had a built-in limit. The radioisotope thermoelectric generators, the RTGs, produce electricity from the decay of plutonium-238. That decay is steady and predictable, but it's also irreversible. Every year, the power output drops a little more. There's no way to recharge it, no way to replace it. All engineers can do is manage what's left, and they've been doing that for decades. Over time, systems have been shut down one by one. First the cameras, then various scientific instruments, then heaters that kept parts of the spacecraft within their ideal temperature range. Each shutdown frees up a small amount of power, which gets redirected to the remaining systems. Right now, only a handful of instruments are still active on each spacecraft, just enough to keep collecting the most important data about particles, plasma, and magnetic fields. But even that won't last forever. By the late 2020s, the available power will drop below the minimum needed to operate those instruments. One by one, they'll be turned off. Not all at once, gradually. Engineers will prioritize whichever instruments are still providing the most valuable data. As long as there's enough power to run at least one, the spacecraft will keep transmitting. But eventually, even that won't be possible. At some point, likely in the early 2030s, there won't be enough power left to run the transmitter itself. That's the final step. Once the transmitter shuts down, the spacecraft won't be able to send anything back to Earth. No data, no signals, just silence. From our perspective, that's the end of the mission. But it's not the end of the spacecraft. They'll keep moving. Both Voyagers are traveling fast enough to escape the Sun's gravity entirely. They're on trajectories that will carry them through the Milky Way for millions of years. Without power, they won't be able to adjust their orientation anymore. Their antennas will drift away from Earth. Their systems will freeze in place, locked into whatever state they were in at the moment the power ran out. But physically, they'll still exist. The structure of the spacecraft, metal components, wiring, the golden record, will remain intact for a very long time. Space is mostly empty, and there's very little to cause wear or erosion. Micrometeoroid impacts could cause damage over time, but the chances of a catastrophic collision are extremely low. So in a sense, the Voyagers will become silent artifacts. Still moving, still carrying their instruments and records, just no longer able to communicate. There's something unusual about that. Most missions end when the hardware stops functioning. Orbiters burn up in atmospheres. Landers stop responding. Probes crash or run out of fuel. The Voyagers are different. They don't have a final destination. No planned endpoint. They just keep going. Long after the last signal is received on Earth, they'll still be out there, traveling through interstellar space. Voyager 1 is heading roughly in the direction of the constellation Ophiuchus. In about 40,000 years, it will pass within about 1.6 light-years of a star called Gliese 445. Voyager 2 is moving toward the constellation Sagittarius with its own distant stellar encounters far in the future. These aren't close flybys in any practical sense. Even at their closest approach, the spacecraft will still be far from those stars. But over cosmic timescales, those are the kinds of distances that matter, and during all that time, the spacecraft will remain largely unchanged. No updates, no corrections, no new data, just motion. It's also worth thinking about what happens on Earth during that time. In 40,000 years, human civilization could be completely different. Technology, languages, even the way we think about space could change in ways we can't predict. And yet, these spacecraft, built in the 1970s, will still be out there, carrying a snapshot of that era, still moving through the galaxy. That's a different kind of legacy, not one measured in data or discoveries, but in persistence. For now, though, the mission isn't over. The Voyagers are still sending signals, still returning data, still giving us direct measurements from a region we can't reach any other way, And as long as that continues, even if it's just for a few more years, we'll keep listening. Because once they go silent, we lose something unique. The only direct connection we have to interstellar space. At least for now. And that raises the next question. What have we actually learned from all of this? By the time both Voyager 1 and Voyager 2 crossed the heliopause, they had already exceeded their original mission many times over. But what they found out there isn't just an extension of what we already knew. It forced a rewrite of some basic assumptions about how our solar system interacts with the galaxy. The first major takeaway is simple. The boundary of the solar system is not clean or static. Before Voyager, models often treated the heliosphere like a smooth bubble, something with clear layers and predictable transitions. Instead, what the spacecraft detected was a dynamic structure. The termination shock wasn't at a fixed distance. The heliosheath was turbulent and uneven. The heliopause itself shifted and behaved more like an active interface than a solid boundary. That changes how we think about stellar systems in general. Because if our sun's boundary behaves this way, then every other star likely has a similarly complex interaction with its surroundings. The second key insight is about shielding. The heliosphere acts as a barrier against cosmic radiation, but not a perfect one. Voyager showed that once you cross the heliopause, the intensity of cosmic rays increases sharply. That confirms that the solar wind and magnetic field are actively reducing the amount of high-energy radiation entering the inner solar system. That matters more than it might seem. It affects the radiation environment around planets, including Earth. It influences long-term exposure for spacecraft and astronauts. And it plays a role in how we think about habitability, not just here, but around other stars. A strong stellar wind might help protect a planetary system. A weak one might leave it more exposed. Voyager gave us the first direct measurement of that effect. Then there's the structure of interstellar space itself. Before these measurements, most of our understanding came from indirect observations, how light from distant stars was absorbed or scattered. That gives you averages over huge distances. Voyager gave us something different, local, direct data. It measured plasma density and found that the interstellar medium in our region is denser than expected. It detected plasma waves that revealed variations over time, showing that even this empty space has structure. It also measured magnetic fields and found that their direction near the heliopause is more aligned with the Sun's field than predicted. That suggests a smoother transition between solar and interstellar environments than many models assumed. Again, not a clean break, but a blended interaction. Another important lesson comes from particle behavior. At the termination shock, the way particles gained energy didn't fully match existing theories. That has implications beyond our solar system, because similar shock processes occur in many astrophysical environments, around stars, in supernova remnants, and even in galaxy clusters. Voyager provided a real-world test case, and the results showed that those processes are more complex than simplified models suggest. There's also the question of scale. The heliosheath turned out to be much thicker than some predictions, stretching across billions of kilometers. That tells us that the region where solar and interstellar influences mix is not just a thin shell. It's a vast zone with its own internal dynamics. That has implications for how energy and particles are transported across the boundary. Then there's the broader perspective. Before Voyager, interstellar space was mostly an abstract concept, something inferred, not directly experienced. Now we have actual measurements. We know the particle densities, we know the magnetic field strength, we've detected plasma waves and tracked how solar disturbances propagate even beyond the heliosphere. It's still just one region of the galaxy, but it's a starting point. And that's important because it grounds everything else. Instead of relying entirely on models and distant observations, we now have direct data from the space between stars. That's a shift. It turns interstellar space from something theoretical into something measurable. There's also a practical side to all of this. Any future mission that aims to travel beyond the heliosphere, whether robotic or eventually human, will have to deal with the environment Voyager is currently sampling. Radiation levels, particle densities, magnetic fields, all of that affects spacecraft design, shielding, communication, and navigation. Voyager is essentially doing reconnaissance. It's mapping out conditions in a region we haven't been able to reach before. And it's doing it slowly, over decades, building up a dataset that no single short mission could provide. Finally, there's the idea of context. Our solar system isn't isolated. It's part of the galaxy, moving through regions of interstellar space that can vary over time. The heliosphere is our interface with that environment. Voyager showed that this interface is active, changing, and influenced by both internal and external factors. That means our local space environment isn't constant on very long timescales. As the Sun moves through the galaxy, it could encounter regions with different densities, different magnetic fields, different levels of radiation. And when that happens, the heliosphere will respond. So what Voyager has really given us is a baseline, a direct measurement of what interstellar space is like right now in our current location. Everything else builds on that, and that leads to the obvious next step. If we've learned this much from two spacecraft moving slowly outward, what could we learn from a mission designed specifically to go even farther? At some point in the early 2030s, both Voyager 1 and Voyager 2 will go silent. When that happens, we lose our only direct sources of data from interstellar space, and right now, there's nothing out there to replace them. That's the gap scientists are trying to solve. For years, researchers have been working on concepts for a new mission, one that doesn't just reach the edge of the solar system by accident, but is built specifically to study it in detail. The most serious proposal so far is called the interstellar probe. The idea is simple in principle, but difficult in practice. Instead of taking decades to reach the heliopause like Voyager did, this probe would travel much faster, aiming to reach that boundary in about 15 years. That means it would need a much higher launch speed, likely using a combination of powerful rockets and gravity assists. Some mission designs even consider using a close flyby of the Sun, a maneuver known as a solar Oberth maneuver, to gain additional speed. By diving deep into the Sun's gravity well and firing its engines at the right moment, the spacecraft could achieve velocities far beyond what Voyager managed. But speed is only part of the goal. The real difference would be in the instruments. Voyager's instruments were designed in the early 1970s. They've performed incredibly well, but they're limited compared to modern technology. A new probe could carry far more advanced sensors, higher resolution particle detectors, more sensitive magnetometers, better plasma instruments, and possibly even imaging systems capable of capturing the boundary region in ways Voyager never could. It could also be designed with redundancy and longevity in mind from the start, based on everything we've learned from managing the Voyager spacecraft over decades. Another key improvement would be trajectory planning. Voyager 1 and 2 are moving in specific directions that were determined by planetary flybys. They've given us detailed data along those paths, but that's still just 2 lines through a much larger structure. A dedicated interstellar mission could be aimed to explore a region of particular interest, perhaps aligned with the incoming flow of the interstellar medium, or targeted to investigate specific features suggested by previous observations. In other words, it wouldn't just pass through the boundary, it would study it intentionally. There are also ideas for multiple spacecraft. Instead of sending just one probe, some proposals suggest launching a small fleet. That would allow simultaneous measurements at different locations, giving a more complete picture of the heliosphere's shape and behavior. Think of it as moving from a single data point to a network. That would be a major step forward. But there are challenges. Cost is one of them. Missions that operate over decades, travel vast distances, and require high-speed trajectories aren't cheap. They also demand long-term commitment, since the most important data might not come back until many years after launch. There's also the issue of power. Just like Voyager, any interstellar probe would need a reliable energy source that works far from the Sun. That likely means some form of radioisotope power system again, but with modern improvements. Communication is another hurdle. At even greater distances and higher data rates, future missions will need more advanced ways to transmit information back to Earth. There's ongoing research into laser-based communication systems, which could potentially send more data over long distances than traditional radio signals. But those systems come with their own challenges, especially when it comes to precise aiming over billions of kilometers. Despite all that, momentum is building. In the early 2020s, studies for the interstellar probe gained support within NASA, especially through decadal surveys that set priorities for future space science missions. These studies outlined what such a mission could achieve, not just in terms of heliophysics, but also planetary science and astrophysics along the way. Because an interstellar probe wouldn't just study the boundary. On its way out, it could also observe objects in the outer solar system. Kuiper belt objects, distant dwarf planets, and regions that are still poorly understood. It would be a multi-purpose mission with the heliopause as its main target. There are also more experimental ideas. Some researchers have proposed using solar sails, large reflective structures that use sunlight for propulsion, to gradually accelerate a spacecraft to high speeds. Others are exploring concepts like laser propulsion, where ground-based lasers push a lightweight probe to extreme velocities. Those ideas are still in early stages, but they point to a broader goal: reaching interstellar space faster and in greater detail. For now, though, Voyager remains our only direct connection. Everything we know about the boundary of the solar system and the environment just beyond it comes from those two spacecraft. That's why there's urgency behind these new mission concepts, because once Voyager goes silent, we won't have real-time data anymore. We'll have models, we'll have past measurements, but we won't have something out there actively sampling the environment. And given how many surprises Voyager has already uncovered, it's a safe assumption that there's still more to learn. The next generation of missions isn't just about continuing where Voyager left off. It's about going further, faster, and with better tools, turning a once accidental exploration into something deliberate. Because now we know what's out there, at least a small part of it. And that's enough to make us want to go back, this time on purpose. What Voyager 1 and Voyager 2 have done goes beyond mapping the edge of the solar system. They've given us context. Before these measurements, it was easy to think of the solar system as a self-contained region, planets orbiting the sun, surrounded by empty space. But what Voyager showed is that we're not isolated at all. We're embedded in a much larger environment, constantly interacting with it. The heliosphere is the key to that interaction. It's the bubble created by the sun, pushing outward against the interstellar medium. But it's not just expanding freely, it's being shaped, compressed, and influenced by the galaxy around it. That means our solar system is, in a sense, moving through space like a boat through water. There's a direction of motion. There's a flow of interstellar material. There are magnetic fields that exert pressure and shape the boundary. And that movement matters, because the region of the galaxy we're currently passing through isn't uniform. The density of interstellar gas, the strength and orientation of magnetic fields, the background radiation environment, all of these can change over time. Right now, the Sun is travelling through a region known as the local interstellar cloud, a relatively low-density area within a larger structure sometimes called the local bubble. This region likely formed from past supernova explosions that cleared out much of the surrounding gas. Voyager's measurements give us a direct sample of this environment. And that raises an important point. What we're measuring now might not always be the same. As the solar system continues orbiting the center of the Milky Way, it will pass through different regions, some denser, some more turbulent, some with stronger magnetic fields. Each of those environments could change the shape and size of the heliosphere. A denser interstellar medium would push harder against the solar wind, potentially compressing the heliosphere. That could allow more cosmic radiation to reach the inner solar system. A less dense region might let the heliosphere expand, so the shield around our solar system isn't constant over geological timescales. It evolves. That has implications not just for space physics, but for long-term conditions on planets. There's ongoing research into how changes in cosmic ray flux might influence planetary atmospheres or cloud formation on Earth. The connections aren't fully understood, but Voyager's data provides a piece of that puzzle, showing how the heliosphere modulates incoming radiation. There's also a broader astrophysical angle. Every star with a stellar wind creates its own version of a heliosphere, an astrosphere. The size and shape of that astrosphere depend on the star's activity and the surrounding interstellar environment. So by studying our own heliosphere, we're learning something about other star systems too. If a star is more active than the Sun, its astrosphere might be larger or more turbulent. If it's moving through a denser region of space, its boundary might be compressed. That affects how radiation interacts with any planets orbiting that star. In other words, Voyager's data feeds into how we think about exoplanets and their environments. Not directly, but through analogy. It helps answer questions like how much protection does a star provide? How stable is that protection over time, and how might that influence the conditions on planets within that system? Then there's the philosophical angle, but grounded in real data. For the first time, we have direct measurements from beyond the influence of our own star. That's a shift in perspective. It's no longer just theory or distant observation. It's something we've physically reached, and what we've found is that the boundary between our system and everything else is not a hard line. It's a region of interaction. That idea scales up. Galaxies interact with their surroundings. Clusters of galaxies interact with larger structures. Boundaries in the universe are often zones of exchange, not separation. Voyager gives us a small-scale example of that principle, and because it's local, we can study it in detail. There's also something practical in this bigger picture. Understanding our position in the galaxy and the environment around us is part of understanding long-term space travel. If future missions go beyond the heliosphere, they'll be operating in the same environment Voyager is sampling now. The radiation levels, particle densities, and magnetic fields measured by Voyager will inform how those missions are designed. It's a first step toward operating outside the Sun's protective bubble. And even though that's far in the future, the data we're collecting now will still be relevant, because the basic conditions of interstellar space don't change quickly on human timescales. Finally, there's the idea of scale. The solar system feels large when you think about planets and distances between them. But in the context of the galaxy, it's tiny. Voyager has traveled for nearly 50 years and is still only a fraction of a light-year away from Earth. The Milky Way is about 100,000 light-years across. That contrast is hard to grasp, but it puts things in perspective. What Voyager has done is extend our reach just enough to cross one boundary, the edge of our Sun's influence. Beyond that, there's still an enormous amount of space we haven't explored, and yet, even that first step has already changed how we see our place in the galaxy. Not as an isolated system, but as part of a much larger dynamic environment. And the fact that we've been able to measure that directly with 2 spacecraft built in the 1970s is what makes the whole story remarkable. Because it shows that even a small step outward can completely change the picture. Right now, without making any noise or drawing any attention to itself, Voyager 1 is moving through interstellar space. Not orbiting anything. Not heading toward a target in the usual sense. Just traveling, carrying instruments, a record of Earth, and the last active connection we have to that region. Voyager 2 is doing the same on a slightly different path. That alone is something new. For most of human history, everything we built stayed on Earth. Then we reached orbit, then the Moon, then other planets, but always within the Sun's domain. Voyager is different. It's the first time we've sent something beyond the environment controlled by our own star. And what's interesting is how unintentional that part was. The mission wasn't designed to be interstellar in the modern sense. It became that because the spacecraft survived long enough to get there, because the trajectory allowed it, because engineers kept finding ways to extend its life. Now, decades later, we have objects that will outlast almost anything else we've ever built. Not because they're indestructible, but because space is mostly empty. There's no atmosphere to cause drag, no weather, no corrosion in the way we experience it on Earth. Over long timescales, there will be impacts from tiny particles, gradual degradation from radiation, but those processes are slow. So the Voyagers will persist. They'll keep moving through the Milky Way for millions of years. Their paths are already set. Voyager 1 is heading toward the constellation Ophiuchus. In about 40,000 years, it will pass within roughly 1.6 light-years of a star called Gliese 445. That's not a close encounter in practical terms, but it's the kind of proximity that matters on interstellar scales. Voyager 2 is on a different trajectory, moving towards Sagittarius with its own distant stellar flybys in the far future. Neither spacecraft will be captured by those stars. They'll just pass through the general region and continue on. Over time, their trajectories will be influenced by the gravitational pull of the galaxy as a whole, but those changes happen slowly. What's more immediate is what happens in the next few decades. At some point, both spacecraft will stop transmitting. Their power sources will drop below the level needed to operate the transmitter. The antennas will drift out of alignment. The signal will fade. From Earth, that will look like the end. No more data, no more updates. But out there, nothing dramatic happens. The spacecraft don't explode. They don't shut down in a visible way. They just continue, silent. That's an unusual kind of ending. Most missions have a clear finish. A crash, a shutdown, a final transmission. Voyager's ending is really just the point where we stop hearing from it. After that, it becomes something else. Not an active probe, but an artifact, still carrying the Voyager golden record, still preserving the state it was in when it went silent, still moving through regions of space we haven't explored. And that raises a different kind of question. Not about physics or data, but about time. The Voyagers will outlast all current technology on Earth. They'll likely outlast many of the structures we've built. Over tens of thousands of years, even continents change, climates shift, civilizations evolve or disappear. The spacecraft won't notice any of that. They'll just keep going. In a way, they're a snapshot of a specific moment, late 20th century Earth, moving forward indefinitely. And while the chances of them ever being found are extremely small, that's not really the point. The point is that they exist, that something built here has crossed into interstellar space and will remain there. That's a milestone. Not because it changes the galaxy, but because it changes what we've done as a species. We've moved from observing the boundary of our solar system to physically reaching beyond it. And even though the Voyagers are small, limited, and aging, they've already done something that no future mission can repeat for the first time. They were the first to leave. Everything that comes next, whether it's faster probes, more advanced instruments, or even human missions far in the future, builds on that step. But this one belongs to Voyager, a pair of spacecraft launched in 1977, still moving outward, still carrying a signal from Earth, for now, and eventually carrying only silence. Subscribe.